So the distance from that center point, let me just open up this. Okay, good. So there's some center point. It's called a C. And there are two ends, right, which is like the maximum distance it would go away from. We refer to this as the amplitude. And the amplitude is just some distance from the center point, right? So it's like some distance from the center point, call that D. So this amplitude is equal to D, right? So now, as this thing is moving, to and from the center point, its position is actually a function of one of our favorite functions, the sinusoids, right? So let's say, okay, we're starting from some point in the center. And we try tracking the change as it moves away from that center, right? So we can pick either side to start. So let's say here, and then we want to go this side. We say it's some small value greater. So here is going to be like a 0 point, and this would be some value 0.2. And just for like simplicity's sake, let's call this here 1, right? 1. So as it moves away from the center, the distance increases, right? Up to some point 1, right? So it's going to move away, move away, move away, move away. Then its value is going to be some point 1. Then it's going to turn around, right? And accelerate this way, right? It's going to come here. It's going to slow down, right? And it's going to accelerate back this way. And then its distance is going to start dropping again, right? Dropping, 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 till it reaches back 0, right? So started at 0, ended up at 1, and then now it's back at 0. Then it's going to start going this way, right? Let's put a 0.2 here, but this is negative now, right? So its distance is going to continue decreasing till it reaches -1. Remember, this thing is symmetrical, right? This here is also D. Right? This here is also D, symmetrical. So it's going to continue going to -1. And then it's going to come back to 0, continuously decreasing. And it's going to continue doing this. So the way we model this is by saying the distance, x, is equal to sine omega t times a, where a is the amplitude, right? Now, a sine wave, we can modify a sine wave, right? Based on just some basic parameters, right? So let me just pull up a graph here. Let's do sine of x, right? Sine of x is like this. And if you were to make some adjustments, right? Like say 2 sine of x, what happens? The frequency changes, right? The frequency changes. And 7, its frequency increases again, and 8, and so on and so forth. And if we were to put some value here, like a, or so a being an actual value, something like 5, you see the amplitude increases. So because all harmonic systems aren't simple, aren't just sine of t, right? Sometimes they vary with frequency, with how fast this particle or the point on the thing that we're tracking is moving back and forth. We need a particular frequency to model this system in a particular way, right? And because the distance they travel from that point isn't always 1, right? It could be anything. That's why we model it with x is equal to a sine omega t, where omega refers to the angular frequency. All right. And that's all there is to creating this formula. Now we know that since this is distance, right? Now let's go back to the handout. Right. Since this is the formula for distance, x is equal to a sine omega t. If we or to differentiate this once, right? Dx dt, we would get velocity, right? So we differentiate that one time using the chain rule. The first derivative of sine is cosine, right? A function within a function, so the chain rule. So we need to differentiate the stuff inside sine omega t, right? Inside the sine function. So the first derivative of omega t goes to just omega, and then we multiply that, right? That's where this omega came from. And then if we do that again, we'll get acceleration, right? So minus omega squared sine omega t, because cosine is minus sine, right? Now, in some books, you might see them modeling distance as a cosine omega t, and that's fine as well, right? They just didn't start from the middle point. And the difference between the sine and cosine wave is just a 90 degrees phase shift, right? Right, it's just that 90-degree phase shift. So they just, this, instead of starting from 0, they started the distance from 1, right? So some books you might see them modeling it with x being equal to a cosine omega t, right? So that's what the formulas, and we'll talk more about them as we go through. Right, so first, we only have 2 questions today, so shouldn't take too long, right? So number 9, first they say define simple harmonic motion, which I'm sure most of you can do. All right. And then they start describing the problem, right? A point starts from rest at a distance of 0.4 meters from the center of its path and moves with simple harmonic motion. If in its initial position and the acceleration is 1.2 meters per second squared, find its velocity when at the distance of 0.2 meters from the center and when passing through the center, right? So from the center and then passing through the center, and B, its periodic time. I think there's probably a typo in somewhere here, right? So, but in its initial position, the acceleration is 1.2 meters per second squared, right? That's it. So first, we need to define simple harmonic motion. Simple harmonic motion, as I said, is that oscillating back and forth through that mean point. More concretely, or more formally, simple harmonic motion is repetitive movement back and forth through an equilibrium or central position, so that maximum displacement on one side of this position is equal to the maximum displacement on the other side, right? Also, simple harmonic motion can be defined as motion in which the restoring force is directly proportional to the displacement of the body from its mean position. So what that's saying is that as we move away from the body, the restoring force, the force bringing back, is proportional to that distance, right? Because that as we go further away, the force pulling it back is gonna increase at this point, right? Until it's completely going backwards. Right? Yeah, that's what. And they spoke a little bit more, and they just gave us just a definition for acceleration. So if in the test, Miss asks you something like this, you just write your own definition, right? Or maybe just one of these definitions, if you can remember. All right, good. So time to do the working. A point starts from rest at a distance of 0.4 meters from the center, right? So 0.4 meters from the center. And the acceleration at that point, so this here would be A, right? That's that distance here, right? AA here would be 0.4, right? Meters from the center. If they say the distance between 2 points is something like 4 meters, then we obviously need to divide this by 2 to get half the distance, right? But 0.4 is the distance from the center. Acceleration is 1.2 meters per second, right? And we need to find the velocity when it's a distance of 0.2 meters and 0 meters from the center. Okay.
Per squared second, sir.
Is second squared? Is that what you're saying?
Yes, sir.
Okay. Okay, good. So we know from just differentiating the distance formula, we have V is equal to A omega cosine theta. Now, V, substituting in as 0.4 is equal to 0.4 omega cosine theta. Now, we don't know omega, but we can find it using this acceleration, right, that they gave us. Because we have some formula that gives us acceleration as a product of that omega and distance. So in order to go about solving this formula, we're going to want to find omega. So just acceleration is equal to omega squared times x. X here is going to be 0.4 because the acceleration that they gave us is 1.2, which is from the initial position, right? Which is 0.4. So plug those values in. We get 1.2 is equal to minus omega squared times minus 0.4. Now, because it's simple harmonic motion, you need to keep track of your signs, right? If acceleration is positive, the distance needs to be negative, right? If the distance is positive, acceleration needs to be negative, right? So that the signs work out. Because if you don't do that, what you're going to end up doing is the square root of some negative number, right? And the square root of some negative number is going to give you some imaginary values. So you don't want to do that. So you want to make sure the signs are opposite. And if you think it through, like draw the problem out and work it out, where you reference these distance and these accelerations from, it'll make sense, right? So these signs need to be opposite each other, right? Good. So this minus out here and this minus in here, right, can cancel out and give us plus 0.4. If it was the other way, if it was minus 1.2.
Sir, do a diagram. Let me see it now, please.
0.4, right? Here, this would be 0.4. This would be minus 0.4 carry over. So it would be minus 1.2 over minus 0.4. So, okay, let me do the diagram. All right. So because it's simple harmonic motion, as I was saying, the way you reference it, you need those signs to cancel out because you don't want imaginary values. So generally, let's say this is the starting point, 0.4 meters, and the acceleration is 1.2 meters per second. If we want this acceleration to be 1.2 meters per second, and this is the general vector for the acceleration, right? This here is positive, this here is negative, right? Here, right? Here needs to be a 0 point. Here needs to be a positive point, which is going to be 0.4 meters. And this here should actually be minus 0.4 meters. So we'll say this is 0.4 meters from the center, and we'll denote it as a negative sign, right? So as this particle moves, right, remember it has positive acceleration. So it's accelerating, 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 right? Here, and it's going to reach this point here, right, which is max velocity, which I'm sure you guys would have read somewhere in the textbook or the handout, right? Max velocity somewhere around here. Now, let's just do that, so draw that something like this, right? Max velocity somewhere there, right? Now at this point, right, because remember, it can't keep accelerating straight up, because when it reaches here, it's going to have to stop abruptly, right? What we wanted to do is reach here, slow down, at 0, and then come back. So from this point on, right, it needs to be decelerating or have negative acceleration. So when it passes this point, it needs to start decelerating, right? Decelerating. So at this point here, it's going to have minus 1.2 meters per second squared. Okay, good. So as this switches over from being a negative number, let's call this negative 0.01, and this positive 0.01, the acceleration and this distance needs to have opposite signs for everything to work out. Okay? Does that make sense?
Yeah, perfect. So,
Okay, so someone's asking, what's the unit for simple harmonic motion? Simple harmonic motion there isn't a unit for it. Simple harmonic motion is a type of motion that has particular properties that govern how its distance moves, how its distance changes, how its velocity changes, and how its acceleration changes. There is no simple harmonic motion constant or anything like that, right? It's not a value you find, it's a concept. Same thing like circular motion, right? Circular motion, right? Circular motion isn't just some value you find, right? You don't find like 5 circular motions, right? It's just like a concept. All right, Steve. So there's no units for simple harmonic motion. So just the same regular units, meters per second squared, meters per second squared, or meters per second in the case of velocity. All right. Good.
So Miss was telling us that we can just drop the negative sign from the omega.
Well, I mean, yeah, but that kind of accomplishes the same thing, right?
Yep.
So you're dropping the omega sign from the omega is the same as multiplying these to making it positive. You can see in a second. Okay, yeah, guys, sorry about that. Just had to take this phone call. Okay, so yeah, as I was saying, right? Because it's mathematics, we kind of can't just go ahead and just ignore the minus sign. That's like something you would tell people without having to explain all the signs and whatever the references and stuff like that. But yeah, if you want life easy, you can just go ahead and ignore that minus sign, right? But technically, what's happening is that they have alternate signs, acceleration and this distance have alternate signs so that they kind of work out all the math work out when we reference it up like this, right? But yeah, you can go ahead and drop that and write this in as positive, which will be accomplishing the same thing, just kind of skipping a step, right? All right, good. So after having that, we of course simplify, right? We end up with something like 1.2 meters per second squared is equal to omega squared times 0.4. Then that just simplifies to 1.2 divided by 0.4, which is equal to omega squared, right? So omega is equal to the square root of 1.2 divided by 0.4. 1.2 divided by 0.4, well, that's just like 12 divided by 4, right? Which is square root of 3. Okay, so square root of 3. Now, after finding omega, we'll use it later on. But for now, we need to find a way to either calculate what t is, which is pretty hard, or find a way to evaluate this part here, this cosine omega t. All right. So we want the velocity at two particular points when x is 0.2 meters from the center and 0 meters from the center or at the center. Okay. Okay. So x is equal to a sine omega t, right? So 0.2 is equal to 0.4 sine omega t, right? Now 0.2 divided by 0.4, well, that's just 2 over 4, which is just a half, which is just 0.5, right? I just plug it into the calculator and you'll get that. So 0.5 is equal to sine omega t, right? Now, if you do a lot of math, you know that there's some basic values in trigonometry, right? 0.5 at sine goes to root 3 upon 2, right, of cosine, right? This here is actually sine of 30, right? So cosine of 30 goes to root 3 upon 2, which is approximately 0.866. Now, you don't need to remember that. What you can do is pretend that this is a unit circle, right? Or a unit triangle, a triangle with hypotenuse 1, right? So something like sine of theta, right? Some value theta is equal to the opposite over the hypotenuse. If you assume this hypotenuse is 1, right, is 1, then we're left with 1 times sine of theta is equal to that opposite, right? Now we can rewrite this saying that the opposite is 0.5, and this here is just sine theta. But we don't have theta, we have omega t. But sine theta is equal to 0.5. If sine theta or sine of something, let's say x, is equal to 0.5, then cosine of that thing, right? Remember the hypotenuse is 1, so we can just go ahead and draw a little triangle here. This hypotenuse is 1, right? The opposite, this here would be a theta, or it would be x, because I just changed the variable. It would be x, this here would be 0.5. 0.5 here would be some unknown, right? Some opposite. Not opposite, some adjacent. Unknown, adjacent, right? Good. So now the adjacent can be described by Pythagoras theorem, which is 1 squared is equal to sum of the other two sides, right? 0.5 squared plus this adjacent squared. Do away with this. Now we can maneuver this. We end up with 1 squared, which is just 1, minus 0.5 squared. Carriers. Carry over square root is equal to the adjacent value, right? Is equal to the adjacent value. Now, this adjacent, right, is still technically cosine of x times the adjacent value of 1, which is just cosine of x. So this here is actually cosine of x. Cosine of x. Now, cosine of x, when we're doing that, we actually mean cosine omega t. So this value here, 0.5 sine omega t evaluates to the it can help us evaluate the cosine omega t using this, right? Using this Pythagoras theorem unit triangle thing. We work this out here, finding cosine omega t as being 0.866, or if you remembered all your basic trigonometric results for like cosine of 30, 45, 60, and so on, you'll just realize that it's root 3 upon 2. All right, good. Now using that, let's go back up, right? We know 0.4, right? We know omega, and now we know cosine omega t. So we can solve for v at 0.2. So it's just a matter of plugging things in. So let me just pull up a trig table. Right, so you guys can have an idea where you get these values from if an easy one happens up here. Right, so these are them, right? And just something you memorize or get used to over time, but essentially says when sine is half, cosine is root 3 upon 2. When sine is root 3 upon 2, cosine is half. When sine is at 45 degrees, both of them is 1 upon root 2, right? Sine and cosine is 1 upon 2. And there are just some other basic things like sine of 0 degrees is 0, cosine of 0 degrees is 1, sine of 90 is 1, cosine of 90 is 0, and just some other oscillating terms, which you'll get used to as you do more math, right? Okay, good. So now having that value, we know cosine omega t is root 3 upon 2, or if you want to write a decimal, 0.866. Plugging those values in, we have v is equal to a omega cosine omega theta, cosine omega t. Plugging the values in, v is equal to 0.4 times root 3. Omega, right, is root 3, which we solved up here. Right, omega is root 3 a while back. Omega is root 3. And cosine omega t is actually root 3 upon 2, right? For 0.2, for x equals 0.2, right? Root 3 upon 2. Simplifying this, right? You just plug the values into a calculator, but you should get something like 0.4 times root 3 times root 3 is just 3, right? Divided by 2, which is just something like 1.2 divided by 2, which is 0.6. Okay, so you guys left with 0.6 meters per second. Okay, good. Now for when it's at the center or a distance of 0 from the center, we end up with x is equal to 0, 0, and a 0.4 sine omega t, right? Now the 0.4 is in carry out, so it'll just be 0 sine omega t. Now you can go ahead and do all the calculations and whatnot, right? But when sine is 0, we know cosine is 1, right? Just get that from your trig table again. When sine is 0, cosine is 1. So we know the value to put in there is 1. So again, we plug in those values, right? Same thing, 0.4 root 3 root 3. But here, instead of root 3 upon 2, we plug in 1. Evaluate this, right? So that should give us v is equal to 0.692 meters per second. Okay. Any questions so far on this?
Sir, is there another method that we can use? I think Miss showed us where you equate that sine square, 1 is equal to sine square theta plus cos square theta, and then we substitute.
1 is equal to sine squared omega t plus cosine squared omega t. Yeah? This?
Yes.
So what this is all this stuff I was talking about, right? This here is called the Pythagorean identity or something. I can't spell that, right? But it's Pythagoras identity, and it's essentially the same thing, right? So let me just go ahead and do that, right? So 1 is equal to 0.5 squared plus cosine squared omega t, right? This is going to go 1 minus 0.5 squared, carry the square over, okay? Omega t. So yeah, so it's the same thing, right? Which is what we have here. Agreed? Same thing.
Yes,
So
sir.
this is just like the foundations and where it comes from. But yeah, you can just as easily remember this identity, the Pythagoras identity, right? From your trig identities and just solve that, right? Or you can remember your values, right? From your tables, if like a basic value pops up, right? Either way works and you'll get the same answer. All right, good. So that there was the hard part, right? The next part is find periodic time. So you guys remember from high school physics or any other time like that, or maybe in this class alone, right? We know that time is equal to 1 upon frequency, or frequency is 1 upon time, right? That basic formula, right? Now, we don't have frequency, but we do have angular frequency, which is omega. And if we divide omega by 2 pi, we'll get frequency. So this is another formula that you may have come across, right? F is equal to omega divided by 2 pi. Or you might come across omega is equal to F times 2 pi, right? Converting frequency to angular frequency. And then you just solve this for F, which is omega divided by 2 pi. Okay, so to solve the time, we need to find F, right? So we're finding F. To find F, we need to use omega and divide it by 2 pi, right? Plugging those values in, finding F is equal to root 3, divided by 2 pi, F is equal to 0.276. Using this to find time, get t is equal to 1 divided by 0.276, which is 3.63 seconds. Right? Alternatively, you can just say t. Right? You can just say t is equal to 1 upon f. Right? F is equal to 1 upon omega divided by 2 pi, right? Which is just 2 pi divided by omega. So t is equal to 2 pi divided by root 3, right? You can just put everything in one and just solve it there, but you should still get the same answer, 3.63 seconds. All right? Any questions? No questions?
No, sir.
Okay. Okay, so number 17 is exactly the same as number 9, right? So what I want you guys to do is to work it and tell me whether or not you get the same answers. All right, good. So first, you want to obtain an expression for the acceleration of a body moving with simple harmonic motion in terms of frequency and displacement from mean position. So we know that formula is acceleration is equal to minus omega squared times x, right? And I showed you guys how to solve that formula, differentiate, right? And this is generated from modeling the motion, right? Okay, so we just start from the top, work down, and you'll get this expression, right? So just simply just proving that expression before you work the problem. Now working the problem, same thing, right? Working the problem, same thing. A body starts from rest at a distance of 3.6 meters from the center of its path with simple harmonic motion. It starts with an acceleration of 0.9 meters per second. Calculate the velocity when 2.4 meters from the center of its path. Calculate also maximum velocity. Maximum velocity is velocity at center, right? And periodic time of the motion, right? So periodic time, okay? Shouldn't be any problem. So take a few minutes and work this question out and tell me if you guys have any issues, right? Good.
No, quero ter mesmo.
New chain.
Legal, Fernando.
Sir, you there?
Hey, yeah. Sorry, I was out a little bit. Yeah, someone was asking a question.
I think you only calculated two things here. We had to calculate something else.
Where do you mean the two things? So velocity at this point, and then maximum velocity, right?
Yes, and then periodic time.
That's it. Oh, I forgot to put in another value here. So
Is it 12.6 seconds?
yeah, 12.6 seconds. That's for periodic time. I got 12.5. 12.5, 12.7. Anything close to this should be fine. So you should get three answers, right? You should get 1.34 meters per second, 1.8 meters per second, and 12.6 meters, not meters per second, 12.6 seconds. Okay.
All right.
This is 10.
Could you go through the Vmax with us?
Okay, yeah. So first things first. Did someone else draw this line here? Okay. So first things first, right? I have it working here, so we'll have to draw it up. So we need a few things, right? So first, body starts from rest at a distance of 3.6 meters from center. So A is equal to 3.6 meters, right? Acceleration at that point is 0.9 meters per second. 0.9 meters per second, that's acceleration, right? Okay, so first we'd want to find omega, right? The same thing like we were doing here, finding omega, evaluating the cosine omega t parts for the formula, and then just solve it, right? So find omega. We know acceleration is equal to minus omega squared times x times x, and x at this point is going to be a, which is 3.6, right? So we end up with minus 3.6. So we end up with 0.9 divided by 3.6 square root is equal to omega. Zero 0.9 divided by 3.6 square root of that is equal to 0.5, right? So omega is 0.5, right? Let's just write that at the top here. Okay. So now we can just go right ahead and find periodic time. We know time is equal to 2 pi divided by omega, which is 2 pi divided by 0.5. Right? So 2 times pi divided by 0.5, which is 12.5666, which is just approximately 12.6 seconds, right? So we can just write that in at the top here again. Comma t, periodic time, is equal to 12.6 seconds, right? Good. Now, V is equal to A omega sine omega t. Right now, we have two distances that we need to calculate for. One of them is 2.4 and the other is 0. Right, so the distance is 2.4 and 0. Right, 0. So at 0, we know it's going to be 1. Right, we know this here is going to evaluate to 1. This is actually
One
cosine.
question, sir.
Yeah.
Let's say we have like two distance, sir.
What?
Let's say like if we have two distance, like what we can do in that case.
If we have two distance.
Yeah.
So how much ever distances you have, you follow the same procedure, right?
I
Right,
mean, like
follow.
if one was like 3.6 and the other was like 2.7 or 4.
You do the same way you do 0.2, right? So 0.2, you do 0.2 is equal to A sine omega t, carry over 0.5 sine omega t, this 0.5 here. You use your identity, square root 1 minus 0.5 cosine omega t, right? So you'll get something like this or like this. You plug that in and you calculate your value, right? So if you had, let's say this here was 0.2, if you had another one that was 0.5 or 0.1, you would just do the same thing again, right? You would, here would be 0.1, 0.1. This here would become 0.25, right? And then you do the same thing, 1 minus 0.25 square, you'll find some answer. And then you just plug that in and then you find a second velocity, which is whatever that would be, right? 0.65 or something like that, right? So you just do that same thing over again for how much ever distances you have. Make sense?
Yes, sir.
Sure. Just remember, it's the same thing we're doing for 0.2 and 0 meters. It's just that 0 meters is easier because it's simple, right? We already know what the answer is going to be. But technically, it's 1 minus 0 squared, which is just square root of 1, which is 1. So we already know it's 1 because we've done it before. It's kind of easy to already just realize it's 1. Right? So this here, at 0 is going to be 1. So this here is just by 1, right? And A is 3.6. 3.6 times 0.5 times 1, which is 1.8 meters per second. This divided by 2, right? Let me just double check, make sure that's one of the answers. Yeah, 1.8 meters per second. Right, so let's just write that in now again, top here. Right, velocity at 0 meters is equal to 1.8 meters per second. All right, good. Now, for the other one, which is 2.4, let me just verify that's the number we're looking for, 2.4. The distance 2.4, so x is equal to A sine omega t. A is 3.6. Keep typing 0. A is 3.6. X is 2.4. Sine omega t. So therefore, sine omega t is equal to 2.4 divided by 3.6. 2.4 divided by 3.6 equal to 0.667. 0.667, which is 2/3, I guess. Let's write it as 2/3. 2/3. Right, 2/3 sine omega t. So therefore cosine omega t is going to be equal to the square root of 1 minus 2/3 squared.
Harmonic Identity. Quite 10 minutes when I'm in. Let them get joint. Yeah, that's the part.
After we get that.
Just at that point, like where you have 2/3 cosine,
Yeah.
just say that we can just put the equation equal to square root 1 minus e squared
Yeah.
equal to
Yeah, that's just the identity thing, right? Remember the whole Pythagoras identity thing we were talking about with the unit triangle and stuff. We could break this down, right? So 1 is equal to sine squared omega t, right? Plus cosine squared omega t, right? So first, notation-wise, sine squared of x, this just means sine of x all squared, right? So that squared there means everything squared, right? That's just like notation here. So when we say 1 is equal to this, so we know sine omega t is 2/3 squared, right? Putting back that squared sign, but replacing the sine omega t plus cosine squared omega t. We can just solve this to 1 minus 2/3 squared, carry the square root over, right? Is equal to cosine omega t, right? Or just jump to this step, right? Because you know what's going to happen because you've worked this question before.
I got just
Right?
one question.
Mhm.
Please go through with us how we got that sine wt is equal when we find the 0 is equal to 1.
When we find the 0 is equal to 1 here.
Yes.
Oh, okay. So here, right, this part here is actually going to be 0. So it's going to be something like this, right? So you can put 0 here, 0, you can square it, you can do the same thing, right? And you'll do 1 minus 0, right? Squared, 0 squared is squared, which is going to be square root of 1, which is going to be 1, right? Right?
I got you.
Good. So it's the same thing, right? Good. So having known all this, or if you're good and you know all your math shortcuts, right? You just say, oh, sine is 0, cosine of what that same thing must just be 1. Right? Good. So this, you want to evaluate this. This calculator here is a bit weird, so but let me try. All right. So 1 minus okay, now let me just do 2 divided by 3. Let me square that, right? 0.44444. All right, let me do 1 minus 0.44444. Right, it's 5.6. So let me do the square root of that, which is equal to, right? So 0.745. 0.745 is equal
That's the
to
figure I
cosine.
used.
Yeah. So then you bring up back that velocity formula, A omega cosine omega t, right? We know V. This is V at a particular point, right? Here is going to be 3.6 still times 0.5, right? Times 0.745, which is that value we just found. Before we just replaced that with 1. So this here is going to be 1.8 times 0.745.
$1.34.
Yeah, which is 1.341, which should be the answer I wrote. Well, there was an additional answer that I forgot to type in, right? Which is 1.34 meters per second. It should be in the handout though, that same answer for question number 17. All right, good. So that's it, right? They're
Another
both,
question.
yeah, go ahead.
So max in this case is when it was at 0. Remember when you draw that
Yeah,
the diagram?
because remember, up until that point, it's accelerating, right? And then when it reaches that point, it starts decelerating. Yeah.
Yeah, that's
All right, any other questions?
Yeah, so can you please go back and I want to get this formula for V max.
The formula.
Yes, sir. For the maximum
So,
velocity.
so it's known that the maximum velocity, right, is at this center point, right? So with simple harmonic motion, I guess I could say to erase all of this working, right? So it's known with simple harmonic motion, as we oscillate between the 2 points back and forth, right? Back and forth, going, coming, going, coming, right? That the maximum velocity is at this point here, right? At a distance of 0, right? So we call this 0, we call this minus 0.4, or we could call this 4, right? As it relates to displacement, right? Good. So let's say, okay, it's coming here, it's accelerating this way. It's going to reach here, it's going to be 0, and then it's going to start accelerating this way, right? So as it accelerates this way, here its initial velocity is something, 0, and then it just slowly accelerates up, right? Velocity increases. So here it's going to be V max. Now, at this point, it can't continue accelerating, right? Because it needs to slow down and reach 0 at this point. So from this point, it's going to start decelerating back, right? And that's just how simple harmonic motion works. The max velocity is here, is at the center. Okay, that's just where the max velocity is, right?
Yes, sir.
Mhm. And also, like, you can look at the formula. So let's say V is equal to A omega cosine omega t. Now, cosine is a function. Let's plot cosine as a function. Whose maximum value is 1. Cosine's value doesn't go higher than 1. It oscillates between 0 and -1. Its maximum value is 1. So if we look at the formula, we know this here is going to be some positive number. This here is going to be some positive number. So magnitudes wise, here to get the max possible value, this needs to be 1, right? It needs to be 1. So we just stick 1 in there. So V max is when cosine omega t is equal to 1, right? So that's just same as multiplying A and omega by 1, right? So that's how we know V max, where V max comes from. Cosine omega t is 1. Because the max possible value for cosine omega t, or any cosine function, is 1, right? Assuming we factor out these here, this amplitude, right? Make sense now?
Yes, sir. See, it's the same formula.
Yeah. Yeah. And also we know sine omega t, when that's 0, then cosine omega t is 1, right? And you can do all your working for that if you want as well, or you just make the jump. Okay. Any more questions? Unless
Just when you're marking it, yes, sir.
I'll mark it before the next one comes out. I'll try and mark it out this weekend. All right. I only marked a few. I noticed a lot of you didn't do the proof. I think it says derive a formula, and not a lot of you did the derivation, right? So a lot of you got 15 out of 20. Right? 15 out of 20. All right. So if you didn't derive the formula, you probably got 15 out of 20 as well, right?
I showed it.
All right. Any other questions? No.
I have one, sir.
Okay.
So the part when you're ready to find the periodic time, which you have to put 1 over the frequency. So how do you move from hertz to seconds like that? Could you like show the unit cancellation or whatever?
Okay, so it comes from the definition of hertz. Hertz is the number of cycles per second, right? So 1 hertz is essentially 1 hertz is 1 cycle per second. So if we assume cycle doesn't have a unit, right? 1 hertz is 1 cycle per second. We could just say that's like the units is per second, right? 1 upon S. So when we do T is equal to 1 upon F, and the units for F is 1 upon S. Well, this kind of flips, so it just be S. So the units kind of work out. So a hertz is the number of cycles per second, assuming cycles are unitless, and cycle is just like a unit, right? Right, some sort of units, right? Just unit. We say it's like 5 per second, right? So the cycles, we don't actually have a unit for them, right? We say like 5 per second. So the 5 would be 5 cycles per second, 5 per second, right? So the units for hertz is technically just per second, 1 over S per second, right? So whatever that value is per second. So when we do 1 upon 1 over S, we just evaluate to S. Make sense?
Yeah, that makes perfect sense. Now that brings me to another. So what happens when we're moving from angular velocity to hertz? How do we move from meter squared, meter per second squared, no, meter per second to hertz?
Angular velocity? No, so this isn't okay. So that's good. That's a good point. So this omega, right? Omega in this case is not angular velocity, right? Omega in this case is angular frequency, right? Remember, omega is just a symbol. Omega is just a symbol. So in the same way, we sometimes use D for distance, and sometimes use S for distance, and X for distance, right? The same way, sometimes we use omega for angular velocity, and sometimes we use omega for angular frequency. In this case, this is angular frequency, omega. Okay?
Oh, that makes perfect sense. Because I had another question after this, but seeing that you just explained, everything ties together. So
Good. So omega is just the symbol, right? Good. Any more questions? No. All right, so I'll mark the test as soon as possible. Remember, I have other work to do as well, so marking test is not really priority right now, but I will get around to it and I'll try to get it to you guys as soon as possible. All right. I'm sure Miss would have sent you guys the solution so you can gauge your own score there as well. All right. Good. So that's all I have for you guys. Enjoy the rest of your day. And I'll email this handout and upload the video when I get time. Right.
Sir,
Yeah.
one question for you. I don't remember missing anything about the exam this week. Is there one?
I don't think so.
All right. Thanks, sir.
I'm not sure. You can ask just to verify. Right.
All right. Thanks, sir.
Good.